Alright, so hi everybody. If we haven't met yet, I'm George from the Stockholm office, and I'm going to introduce you to one of my favourite hobbies, which is the board game Go, mostly selfishly so that we can all play some Go for the rest of the weekend. So Go is an ancient Chinese game. It's been played in almost the exact same form for more than 2,000 years, but despite it being really old, it's still, people are finding new strategies and new approaches to the game all the time. It's a really deep and fascinating game. And the reason that I like it, and the reason I think a lot of you might like it, is that it appeals to the same part of my brain that likes programming. So the rules of this game are simple enough that I can teach them to you in a lightning talk in less than 10 minutes. But the strategy and the kind of things that come out of that are very complex, and you can kind of take it as far as you want. There are people who play this game professionally and make enough money to live very well. So maybe this is a new career for someone. But as with programming, there are kind of abstractions. So from these simple rules, I'm going to show you some of the kind of emergent properties and emergent behaviors that you can then think about at a higher level, and there are even higher levels than this. So how does the game work? First, you need a Go board. It looks like this. This is the one we'll all be playing on later. And first, the black player will place a stone on one of the intersections on the board, like that. And then the white player will place a stone, and so on. And each player is trying to surround more empty territory, more empty intersections than their opponent can surround, until both players agree that the game is over. They just agree that there are no more useful moves that I can make, so I'm going to stop. But what's to stop your opponent from just putting a stone into your territory that you've surrounded? Well, it's not an entirely peaceful game. Each stone has liberties. So this stone has 4 adjacent empty spaces. That's 4 liberties. If the white player were to play next to this stone, that takes away a liberty. The stone's now in danger of being captured and taken off the board. Maybe the black player ignores it and plays somewhere else. The white player takes another liberty and another liberty. This stone's now down to 1 liberty. That state in Japanese is called atari. If you're a fan of retro gaming, you might know that that means to hit or strike. And when the white player takes away that final liberty, the stone's captured and taken off the board. And at the end of the game, when you're counting up points, the white player gets to take that captured black stone and put it into black's territory to reduce the size of it. But stones, if they're next to each other, they share liberties. So this group of 3 stones here has 8 liberties. So if you keep your stones well connected, it's harder for your opponent to capture them. So let's look at a larger group of stones with more liberties. This group has 12 liberties. But the one in the middle that's labeled 12, the white player couldn't play there immediately. That would be suicide. They would lose their stone. So that's an illegal move. What they'd have to do instead is take away the 11 liberties on the outside first, and then finally take away the one in the middle, if I could use this software, and capture the group like that. Now this is one of the abstractions that I was talking about. This is called an eye. Whenever you have a hole in a group that would be suicide to play in and you have to play there last, that's called an eye. And when you end up with a group that has 2 eyes, there's another interesting property that emerges. This group can no longer be taken off the board. These stones are now unconditionally alive. They're there for the rest of the game. Because if the white player surrounds the group entirely, there are these 2 different eyes, labeled A and B, that are left. And the white player can't play at A because the group still has a liberty at B, so that would be suicide. They can't play at B because it still has a liberty at A, that would be suicide. So now we can finally answer the question I asked, what's to stop your opponent just playing in the territory you're trying to build? Well, because you can stop your opponent from getting 2 eyes and just take all their stones. But if they manage to invade your territory and make 2 eyes, then their stones aren't going away and you've lost your territory. So there's a lot of back and forth and a lot of strategy that goes into making that happen. There's one more rule, and then you'll know all the rules of Go, and we can have a game. This is the rule that there is no recursion in Go. You can't return the board to a position it's already been in. So if the black player takes this white stone, then the white player can't now just take us back to the previous position. Otherwise you get into an infinite loop and it would be a very boring game. So the white player has to go play somewhere else. Maybe the black player plays somewhere else, and now white can take that back. And now black can't immediately return us to the same place before they've played somewhere else. And then maybe white fills in the hole and stops them taking it back. This kind of situation leads to some really dramatic fights in games of Go. both players want to be the one to fill in the hole and get the solidly connected group of stones. So they both go and play really aggressive moves in other parts that their opponent has to respond to, and then they get to come back and replay the recursion. This is called a ko. And that's the rules. You now know all the rules of Go and a little bit of strategy. So it's time for your first Go problem. Going to be some audience participation. It's White's turn. Where should the white player play if they want to kill these black stones? If they want to take them off the board?
Middle.
Middle, yes. See, if the black player gets the spot in the middle, this group has 2 eyes and they're unconditionally alive. But if the white player gets the spot in the middle, it's only got 1 eye and it will never survive. So there's a lot of kind of shapes and pattern recognition, lots of things that we think about in programming a lot of the time manifest in this game. One more abstraction I'd like to show you. This is one of the more famous shapes in Go. This is called a ladder. And this white stone, even though it still has a liberty, this white stone is dead. There's nothing the white player can do to save that stone. Oops, it's black's turn. So if white plays here, then black can still just reduce them to 1 liberty. And then white tries to escape, but they still get reduced to 1 liberty. And then white tries to escape, but they still get reduced to 1 liberty. And these kind of shapes and patterns happen a lot in real games of Go. But then maybe the white player managed to get a stone over here sometime, and now they can escape this if they build out that way. So you have to kind of be seeing how different parts of the board relate to each other and how things are going to grow and change and move towards each other. It's a great game. I want to play. That's it.